Hello, am I audible?
Yes, sir.
Afternoon, everyone. Sorry for the delay. I've been having internet trouble, so I had to switch to mobile internet again. But otherwise, I think right now I have a stable connection. Okay. Today's lecture is rather long. I'll try to chat to go through everything as much as I can. I cannot promise I'll finish the lecture, but at least I'll be able to more thoroughly and in more detail go over thermodynamics and thermochemistry. Okay? Sige. And as you all know, the thermochemistry won't be covered in your midterms this Saturday, but obviously it will still pop up in your final exam. Okay? And today's lesson, hopefully with what you take up, you'll be able to then at least further go into your module work to help you answering the last two items of your problem set for module 2. Okay. It's like a bajillion slides we have to take up, but yeah. So if we're all ready, can I get a thumbs up? Okay, great. Let's do some easy stuff first. Is the physical world static? No, right? Matter is constantly changing, reacting physically and chemically, di ba? In fact, even just like say the physical changes you can observe through our weather, through the water cycle, water evaporating, water precipitating and raining, water flowing about, water dissolving things. These are all physical changes we see. And then chemical changes around us, like the carbon cycle, which changes the forms of carbon, like carbon dioxide into sugar in photosynthesis, and then us and animals breaking down the sugar and releasing back carbon dioxide via respiration. We are also combusting fossil fuels like gas, creating more carbon dioxide, etc. So all of these are chemical changes that we can observe. Let's skip this part now. Now, what enables all of these physical and chemical changes? What powers this? That is energy. Okay. Energy is the capacity to supply heat to something or to do work to something. And there are two main types of energy: potential energy, which is based on relative position, composition, or the condition of an item. So water on top of the mountain, right before it goes down in a waterfall, has a lot of potential energy, gravitational potential energy. The water that's flowing, let's say, down a waterfall has a lot of kinetic energy. Uh, Now, why is it that we're taking up energy in chemistry? It's important to note that matter and energy are interlinked. And in fact, if you think about the Big Bang Theory, the origin of our universe was once all the energy and all the matter of the universe just condensed into a singularity, into a single point. All that we are and all that we have been all came from a single point. And even especially if you go into higher chemistry, into higher physics, you know that matter can also turn into energy. E equals mc squared, the theory of relativity, ni Einstein. And if you know your advanced quantum mechanics, you know that the building blocks of matter, which are the atoms, the neutrons, the and the protons, electrons. Okay, some of these, and then the neutrons and the protons are made up of quarks. And the electrons are almost like a type of quark, but not quite. These are all just packets of energy. And the light, which we experience, which is actually particles called photons, are also packets of energy. So matter is just packaged energy. No? Now, let's go back to our Big Bang Theory story. So everything was once the same point of all matter and all energy at this one point, the super condensed thing that exploded. Because everything came from that finite beginning, we can assume that the total mass and energy of our whole universe is constant. And that's why we have the law of conservation of matter. That's why we have balanced chemical equations. But that is also why energy, we can say, is neither created nor destroyed. We know that energy always just changes forms. The different types of potential energies, it will interchange to different types of kinetic energies, etc. Okay? Are we all following so far about the theory of what we're taking up? Are we still good? Can I get a thumbs up? Okay. Now that idea of energy never being created nor destroyed, of being constant through the whole universe, and only changing forms, is basically what we call the first law of thermodynamics. So let me play this video for everyone to watch. Oops, sorry.
So here I have a balloon filled with hydrogen. It has a lot of chemical energy as hydrogen gas, and when mixed with oxygen, it's a very potent fuel. By igniting the balloon, I add energy and I set.
Rinig ba yung audio? Does everyone hear the audio of the video? Okay, sorry. Let's resume the video. I can't seem to.
So here I have a balloon filled with hydrogen. It has a lot of chemical energy as hydrogen gas, and when mixed with oxygen, it's a very potent fuel. By igniting the balloon, I add energy and I set off a reaction between the hydrogen and oxygen that releases a lot of energy in the form of heat. The conservation of energy is one of the fundamental principles of our universe. Simply put, it says that in a closed system, energy cannot be created or destroyed. It can only be transformed from one form to another. The first law of thermodynamics takes this idea and modifies it for thermodynamic systems. It relates the internal energy of a system to the amount of heat added to the system and the amount of work done by the system. If we look at the explosion again with a thermal camera, you can see quite clearly how hot the explosion was. But the total amount of energy in the room is the same as before I blew up the balloon. It's just changed from chemical energy in the bonds to heat energy. Historically, this idea of turning heat into useful work was the main driver behind the formulation of this law. At the beginning of the Industrial Revolution, both scientists and engineers were creating steam engines in the hope that they could harness energy to further society and industry. The advantage was that they could automate some jobs and match, if not exceed, the power of the human labor force. Steam engines are based on the idea of heating water under pressure until it becomes steam. As it's heated, it expands and pushes a piston that produces mechanical work, be it moving a train or pumping liquids or any number of other functions. Blowing up hydrogen balloons is fun, but the conversion of chemical energy to heat isn't particularly useful. But what we could do is put it to good use in something like a rocket. In physics, work is done when a force is applied to an object and that object then moves a distance. One of the simplest ways of making this hydrogen do work for me is to build a rocket. The hydrogen and oxygen fuel mixture is exactly the same as with the balloon, but whereas the balloon expanded outwards in all directions with the explosion, The rigid walls of the Pringles can funnels the energy in one direction. The chemical energy is then converted into heat and kinetic energy, and by moving the rocket forward form. Rockets are useful if you want to send someone into space, but if I want to use my hydrogen for a more terrestrial use, then I'm going to have to harness the energy in a different way, or transform it to a more useful form. What I've done here is attach my rockets to a wheel, and when it spins, it's doing work as the rockets move around. Now what I can do is attach a dynamo here, which when the wheel spins will convert this kinetic energy into electrical energy, which I can then store for later use. The problem with this is that all throughout this process, you're losing energy in the form of heat to the room, rather than using it to do useful work. Because of this, it's actually a rather inefficient system. While no energy is destroyed, because it can't be, too much of it is lost into the room as heat energy. This issue isn't one that's just isolated to my rocket contraptions, but the issue of efficiency, which is trying to get more useful work out of the same energy input while battling energy loss, is one that's as important today as it was during the Industrial Revolution.
Okay, I hope that was something you guys learned from. So basically, yeah, what we're all trying to do is use energy and make efficient as possible the conversions of energy that we use. Because yes, energy will always change forms, but it's the type of energy into which we can change something to that matters. No, so in the case of, let's say, our modern world, we want to turn as much of the chemical energy, chemical potential energy inside the fuel, for instance, like hydrogen or gasoline, um, into as much of the useful energy, like kinetic energy of moving our cars or launching a rocket. Okay. Now, when talking about how energy flows, okay, and how energy flows, let's say for changing a state in matter, for changing a making a reaction occur, we have to remember that energy can either be released to create a lower, more stable energy state, or sometimes, given a certain system, energy can also be absorbed to create a higher or a stored energy state at the expense of something else. So let's look at these changes. In the chat box, tell me if energy will be absorbed or released if I go from ice to water. So if I melt my ice, what do I need to do to melt ice? Do I have to put in energy or do I have to remove energy from the ice? I have to put in. Okay. So is water a higher energy state than ice or a lower energy state than ice? Water has a higher energy state than ice. Okay. What about if I start from water vapor and it condenses into liquid water? So from vapor to condensing to water, do I have to put in energy or do I have to remove energy from the system? So the system has to remove energy from itself or release energy. Okay. That means that water vapor is a higher or lower energy state than liquid water. Exactly. Did everyone follow so far still? You get a thumbs up on energy states? Okay. Sometimes the change is very mundane. No, sometimes you won't even see an actual physical change like change in form. Sometimes you have water that's 25 degrees Celsius and water that's 60 degrees Celsius. So from normal room temp water to hot coffee water. Diba? Sometimes the energy changes that boring. You have room temp water gaining energy to become hot water. Okay? All the still boring or not, they all involve either a release or an input of energy. Okay? These energy release or input, so remember when I say higher or lower energy state, we can actually put them or draw them in what we call energy diagrams. So this is an energy diagram. We have one state, for instance, the state of my car with its full tank of gas. So all of the energy is actually in that fuel of the gas, no, the chemical energy. And then eventually the car will combust, so the fuel will release its chemical potential energy, and the combustion of the fuel, the chemical reaction, produces or pushes the pistons of your engine and makes your car move. Okay, so now there's less potential energy in my system because now the fuel is being burned. But what happens to that change in potential energy? So burning the fuel and remove or getting rid of that chemical potential energy, what happens to that potential energy? It turned into kinetic energy that's powering your cars. Exactly. So the same thing, diba? You eat sugar and you breathe in oxygen. What do you do to power your body? And then you breathe out carbon dioxide and water vapor. You also pee out the water. But from high chemical energy to low chemical energy or potential energy, what happens to that energy that was transformed? It turns into the energy that lets you grow and move and live. Okay? And sometimes the flow is the opposite. Diba? You'll have low energy carbon dioxide and water, and it turns into high energy sugar and oxygen. How can this reverse process happen? So if breaking down sugar is something that releases energy and powers us humans, how does the reverse process happen? Going from low to high energy. Absorb energy, sabi ni Ella sa chat. And, sorry, wait. Wait. Sorry, I have to pause. Hello? Okay. There was issue with hosting kasi. So I was seeing the chats on another device. So yes, the system has to absorb energy in order to go into the higher chemical energy position. Question, where does the energy come from for this process if it has to absorb energy? From the surrounding, but specifically where? Yes, from the sun, from sunlight. Okay. Now, Thermodynamics is the study of heat and its transformations. And thermochemistry is a specific branch of thermodynamics where we look at the heat energy involved with chemical and physical changes. So it's the specific to chemistry part, whereas thermodynamics can be in chemistry, biology, physics, everywhere. Okay? So we look at when energy is transferred from one object to another, appearing as work or heat. Now, for our work, we must define what a system and what a surroundings, what it means. No? Because someone, I think it was Ella who messaged me, saying that it came from the surroundings. So, what exactly is a system or a surroundings? We must define the system. So, a system is anything that we define it to be. So, let's pretend we're studying a certain chemical equation or reaction like photosynthesis. Carbon dioxide plus oxygen becoming sugar, becoming carbon dioxide and water becoming sugar and oxygen. That entire chemical equation, so those specific molecules involved and atoms involved in that chemical equation or reaction is our system, which means literally everything else in the universe becomes the surroundings, which might include the water in which that's all dissolved in, the cell in which it occurs in, or the organelle, the cell, the whole universe. Those automatically become the surroundings. Okay? And when studying thermodynamics, we usually study the energy changes of a particular system. So a while ago, I was asking you guys about water from melting from ice to becoming liquid water. We were defining that water to be our system. And when I was asking you, what happened? Did the system gain energy or lose energy when it melted? We were looking at the internal energy of that system, of the water. Okay? So with any change, like water melting or carbon dioxide becoming sugar, with any change we observe, physical or chemical, there's always going to be an associated change in internal energy of that system. Note that internal energy is often noted as E or U, depending on the textbook you use. Okay? So internal energy is the total of all the possible types of energy present in a system, including quantum mechanical energy, potential energy, all these different things found in every nook and cranny of your molecule. Okay? And E itself or U is almost impossible to measure. But it's very easy for us to measure the change in energy. That's why we add the delta U or delta E. Okay? And the change in energy of a system depends on the amount of heat that the system will give off or absorb. But it also depends on the amount of work the system will do. So like a while ago, our hydrogen Pringles rocket did work. Diba? The hydrogen gas exploding or combusting did work. It allowed for the can to move a certain distance. Okay? The total energy of the universe is delta U universe. And according to the first law of thermodynamics, the change of energy in the universe will always be zero because all the energy of the universe is finite. There's a finite amount of energy. Okay? So this is the mathematical formulation of the first law of thermodynamics. The change in energy of the universe is zero. Are we still following so far? Are we good? Okay, great. So again, determining the absolute energy of a system internally or even is so difficult. But determining the change of energy in a system is very easy. All we need to do is to look at the amount of heat transferred into or out of a system and the amount of work done on or done by the system. If the system is heated, so we put heat into the system, Q will have a positive value of energy. If the system does work on a substance, meaning we compress something, then we have a positive value for work. But heat can also be released by a system. So it's the energy goes out of the system. It will have a negative heat value of energy. And sometimes the system itself will do work. So in order for the system to do work, it needs to burn its own energy. So when the system does work, it will have a negative work energy value. Okay. So let's go over heat and the work in a little bit more detail. Heat is the transfer of thermal energy between bodies of different temperatures. So heat flow is actually a redundant term, but we hear a lot about it, the flow of heat, no? And it goes always from something that's very hot to something that's very, very cold. Okay? By putting heat into a system, we make something hotter, so we increase the amount of thermal energy and its temperature. We remove heat from something, we can make a substance colder or lower its temperature. Okay. When the amount of thermal energy in different things are the same, no? Or if the temperatures of those substances are the same, then heat will cease to flow between those substances. When talking about heat flow, we also have to come up or use these terms, no? We use the term exothermic or endothermic processes. So exo simply means the system is releasing heat. So heat is escaping the system, and endothermic means heat is going into our system. So our system is gaining heat energy. Okay. So this example here, wherein I have hot water, okay? We know that hot water has high heat energy, has a lot of thermal energy, diba? And then what happens to our system? Eventually, the glass of hot water, a beaker of hot water, will eventually cool down. That means that the heat energy stored in the hot water of my beaker is lost to the surroundings. So it cools down, it loses thermal energy or heat, and it becomes room temperature water. So this is an example of an endothermic or an exothermic process. So hot water becoming room temp normal water. It's an exothermic process. So it releases heat energy. And where does the heat energy go? It goes to the surroundings, exactly. Now let's look at another process. I have a beaker full of ice. It's very, very cold. Okay? So initially, and then eventually, what happens to your beaker full of ice? Diba? If you leave it sitting for a while, all the ice will melt and it will turn into room temperature water. For that to happen, we need to put in heat. Diba? In order for the little molecules of water in ice form stuck in one place, in order for them to have enough kinetic energy to start moving around as liquid, no, when molecules that are not tightly held together. So there's a gain of kinetic energy to go to our final state. So because there's a gain of kinetic energy, by adding in heat, Is this an endothermic or an exothermic process? It's an endothermic process. And so we have to put in heat. And where does the heat again come from? Where does that heat? It comes from the surroundings. It comes from the hot air around you in your room, diba? But the total energy of everything, meaning our system and the unit and the surroundings, will remain constant. Zero, diba? The change in energy of the universe is still zero. Now, the most boring form of heat is heat that's just used to heat something up, to make it cold to something hot. Diba? Sir, is the beaker considered as the system or the surrounding? You can do either, Ella. It depends on us. So if you want to focus strictly on the water, on the ice, then the beaker is part of the surroundings already. And so as the ice melts, the ice will get heat from first the beaker, because that's where it's touching, diba? Because even the beaker is changing temperatures, right? The beaker starts off as a cold beaker touching ice, and then eventually the beaker becomes a room temperature beaker touching room temperature water. So we can think of the beaker as part of it, but we can also the beaker as part of the surroundings. As chemists, we're always just concerned with a particular system that we write in an equation. So for example, here, the equation, if the equation is H2O solid becomes H2O liquid. So this is a chemical equation, although it's not a chemical change, this is just solid to liquid. Pero yon, diba? Ang system natin is defined by the equation, which means then that the beaker is now part of the surroundings. As physicists, they do something else. They look at the whole thing, diba? Pero tayo kasi as chemists, we look at what's described by the equation. Okay? Okay, sorry, let's go back to the boring stuff again. Even without any physical changes like melting or freezing, let's just look at normal changing of temperature. Like normal room temp becoming hot water or hot water becoming room temp water. Ganun ka boring. When dealing with just changes in temperature, we need to talk about heat capacity of substances. And heat capacity of a body of matter, anything, a human has heat capacity, a cell phone has a heat capacity, water has a heat capacity. It's just the amount of heat energy required or to be absorbed or released to change the temperature of a substance, of that thing, by 1 degree Celsius or 1 Kelvin. Okay? So heat capacity is written as a big letter C. So let's look at this example. I have here 2 pans made of cast iron. And by your experience, which of these 2 pans, the small pan or the big pan, will take a lot more energy to make it a hot pan? Like say to make it a 100 degrees Celsius pan. The big pan, no? You need to, 'di ba? If you can imagine, the big pan, kailangan matagal mo siya ilalagay sa stove para siya uminit. Okay? The small pan can heat up very, very quickly. So what does that mean? It means that the heat capacity of the large pan is greater than the heat capacity of the small pan. It will take more energy to make the large pan hotter, or to even just raise the temperature of the large pan by 1 degree Celsius. Now, more important in chemistry, rather than just heat capacity, is something we call specific heat capacity. And specific heat capacity is the amount of heat required specific to a substance or material to raise to heat up or cool 1 gram of that substance by 1 degree Celsius. Okay? And so the amount of heat, Q, equals CM delta T. Okay? So, ganyan siya. The specific heat capacity of the large cast iron pan is exactly the same as that of the small iron pan. It is because they're both made of exactly the same material called cast iron. Is that clear? So substances will each have their own kind of specific heat capacity measured in joules per gram Kelvin or joules per grams degree Celsius. Again, Kelvin and Celsius will have the same magnitude, so same interchangeable sila. Okay? So how do we read this? Kunwari, iron. It will take 0.450 joules of energy to heat up 1 gram of this iron, increasing its temperature by 1 Kelvin or 1 degree Celsius. Okay. So here are more tables for that. Okay. So to calculate the amount of heat required to change the temperature of a substance is easy. Q equals C times its mass times the change in temperature you want it to experience. So delta T is T final minus T initial. So let's try this out. I have 8.0 times 10 to the 2 grams of water, and I want to heat it up from 21 degrees Celsius, cold water, to 85 degrees Celsius, scalding hot water. How much heat does the water absorb to become that temperature? So we will use the formula, Q equals C times M times delta T. The specific heat of water is 4.184 joules per gram Celsius or Kelvin. The mass of water is 8.0 times 10 to the second grams. And then the change in temperature was 85 degrees Celsius minus 21 degrees Celsius. Kapag change, guys, okay lang na Celsius ang ginagamit. But if you have to use temperature in any other way without a delta, we have to use Kelvin always in chemistry. But the change in temperature in Kelvin and in Celsius are exactly the same. So this is fine. Calculating all of it, we will get a Q of 2.1 times 10 to the 5 joules. So Q is a positive value. What does that mean? That heat energy enters water or heat energy exits the water, is released by the water. So heat must be absorbed by the water, kaya siya positive value. So this is an increase in the heat energy of our water. Okay? Now, aside from heat, the internal energy of a substance is also dependent on work. And a special type of work that we'll consider in chemistry is called expansion work or pressure volume work. Simply put, if the system expands, so kunwari, a chemical reaction creates a gas. So the gas that it creates will then push a piston against the pressure of our atmosphere, for instance. So our system starts to create a gas, and the gas push the piston upwards. So if the system expands and pushes up a piston, it does work. So yung system, yung chemical reaction natin had to do work. Does that mean that it will gain energy or lose energy? When you have to do work, when you have to push something yourself, you will lose energy, mapapagod ka. So ganun din yung chemical system natin. If the system has to push the piston, if the system has to expand, like how the combustion of hydrogen had to expand and push the Pringle rocket upwards, that's as if it was pushing on the Pringle, no? That's like the piston. Then the system did work. It loses energy as work. So minus work. If we do the opposite, and we compress a system, we push it and compress it, then we're doing work on a system. So it's a positive, we add energy to our internal energy as positive work. Okay? So this is an example of a system losing energy as work. I have here hydrochloric acid and zinc solid. If you remember our module 2 experiment, diba? The balloon, remember? So let's pretend that the piston is the balloon. So the system, after the chemical reaction, creates hydrogen gas, which inflated our balloon. So you can think of the balloon as the piston. So as the balloon inflates, it's the piston that's being pushed away. So did the system gain energy or lose energy as from work? It loses energy because it had to do the work of pushing the piston or expanding the rubber balloon. Is that clear to everyone? Okay. Now, the change in energy depends on a lot of factors. So it depends on the work, it depends on the heat transfer. And depending on the sign, whether the heat was added into the system or released by the system, if work was done to the system or by the system, then you'll have different levels of change of internal energy, delta E. Okay? Sorry, dapat malaking E yung sa surroundings. So again, remember, the change in energy of the universe is just the change in energy of the system plus the change in energy of the surroundings. And because of the law of thermodynamics, the change in energy of the universe is zero, which means the change in energy of a system equals the negative change in energy of the surroundings, or vice versa. If my system gains energy, that energy was taken away from the surroundings. Diba? Such as when ice was in my beaker was just melting in a room. The heat that melted the ice came from the room, from the air around the room, etc. So these are just some of the measurements of energy. Again, we took this up before, so I'll forward that up. Okay, I'll skip this problem for you guys. You can do this on your own. I'll post na lang my slides. So this is just counting whether energy was done on changing energy. So was heat added to or released by the system? Was work done by or to the system? Okay. Here in chemistry, we're not so much really dealing with work. Now, it's very rare that a chemical system does work, but we are very much interested in the heat associated with any physical or chemical change. And that is what we call enthalpy. Okay. Now, this is how enthalpy is derived. I will skip this part, but essentially, the change in enthalpy or delta H of a system is also its change in internal energy, which is also its heat. Because we assume nga that some reactions do not involve gases. So some reactions just happen in solution. Sometimes reactions have gases, but the change in number of moles of gases does not change. And that sometimes, even if there is a change in number of, or we do create gas or consume gas, the heat contribution of a change in the energy of a reaction is way greater than the work contribution. Okay? So the change in enthalpy is essentially the change of internal energy of your system, and it's again associated with the heat of that physical or chemical change. So chemists usually perform experiments under constant at normal atmospheric pressure, diba? Um, and with that, yun nga, the work is negligible or cancels out. When talking about enthalpy, we're talking about heat. Again, we talk about endothermic or exothermic processes. So ganun rin. Initial state of either reactants or a certain substance losing energy and becoming lower in enthalpy to become its products. Then you have an exothermic process. And then sometimes you have something like, let's say, boiling water, which is a physical change. Lower heat, absorbing heat becomes a higher energy state, such as gaseous water, steam. Then we have an endothermic process. Now, sometimes the heat involved in a chemical reaction or in a physical change is actually shown as one of your reactants or products. And as such, you can determine if the process is endothermic or exothermic. So in the first one, in our first process, the energy shown in kilojoules is in the product side. That means that heat was absorbed or heat was released. So it's one of the products created by the process. So is letter A an endothermic or an exothermic process? It's an exothermic process. No? The second reaction is just actually a physical change. No? You have heat energy as 40.7 kilojoules shown as one of the reactants. So here, is heat absorbed by the system or released by the system? It's absorbed, not to create the gaseous water, which means, is this an endothermic or exothermic process? Endothermic. Great. Okay. So ganyan siya. Now, that's very rare that we will show the energy as part of the reactants or the products. Usually they do that for general chemistry students, just so you can visualize it. What really is often shown for all of us is a thermal-chemical equation that shows a balanced equation, or in a certain form, sometimes sometimes it is shown with fractional coefficients, and that's for a certain reason. And each chemical change or physical change will be given or labeled with a delta H value, the change in enthalpy associated with that balanced equation. And it's the amount of heat associated with the reaction as written, which means it's negative 286 kilojoules that's released because it's negative when half a mole of oxygen reacts. Yet, or when 1 mole of water is created. Okay, so this energy value here is for this as written. If the direction of the chemical equation is reversed, we must also reverse the arithmetic sign of delta H. So kanina, we had this equation, right? It's an exothermic process because it releases minus 286 kilojoules, so the system will lose 286 kilojoules of energy. But if I reverse the process and make it water turning into hydrogen and oxygen gas now, so if I flip the entire reaction, what happened to the sign of delta H? From negative, we reverse its sign to positive. So the reverse process is endothermic or exothermic? It's now endothermic. Okay. Aside from that, like I said, that amount of energy is exactly for the amounts as shown in the chemical equation. So 1 mole, 1/2 mole, 1 mole. But okay, what if I want to do it, or what if I want to look at the energy change if I have 2 moles of H2, 1 mole of O, and 2 moles of water? What do I have to do to my enthalpy change? Because everything was multiplied by 2, the enthalpy should also be multiplied by a factor of 2. If I only want to deal or study 1/4 mole of oxygen, then I have to multiply everything by 1/2 to get the amount of energy that's released by just half of that original amount. And you can solve for any change in enthalpy using stoichiometric ratios. No? So what if instead of 1 mole of hydrogen, it's 5.73 moles of hydrogen? How much energy will be released? So if it's a weird number, if I have 5.73 moles of hydrogen gas reacting in this manner, how much energy will be released? How much heat? What do I do to negative 286 kilojoules? I have to multiply this by 5.73. Okay? Exactly. Ganun lang siya. Proportional lang siya. Please, please be very careful. The delta H of a reaction depends on the physical states of all the substances, reactants, and products. So note, in our particular reaction, the product was liquid water. And iyan yung kanyang associated delta H. If I, for a paper or a book or any other thing, for some reason, nag-iba yung state ng water, kailangan gas yung water na product, look different, right? Different energy requirement. So be careful with that. Pay close attention to all the states. If it's gaseous, liquid, if it's aqueous, if it's solid, etc. So these are the times when we really have to show the states of matter. Okay, let's try this problem out. A gummy bear contains sucrose, and I don't know if you've ever seen a YouTube video wherein they add gummy bear to a chemical called potassium chlorate, and then the gummy bear starts exploding. So let's pretend that the gummy bear was shown to react with 7.19 grams of potassium chlorate. And in doing so, we were able to measure the release of 43.7 kilojoules of heat. And the chemical equation is as follows. 1 mole of sucrose reacts with 8 moles of potassium chlorate, and it creates carbon dioxide, water, potassium chloride, and it releases heat. So first, we solve for the number of moles of potassium chloride that reacted. We'll use its molar mass. So that's 0.0587. And then to determine the amount of heat released per mole of the reaction, okay, sorry, per mole of potassium chlorate, we need to then divide the amount of heat released that we observed or measured in the reaction by the number of moles of potassium chlorate. And that gives you the reaction having 744 kilojoules of heat released per mole of potassium chlorate reacted. Now, because the equation as written represents the reaction of 8 moles of potassium chlorate, diba? 1 is to 8 is creates 12 and carbon dioxide 11 water and 8 KCl. To get the proper enthalpy of this reaction as written, we then have to multiply the whole equation by 8 moles of potassium chlorate. So this is the energy change associated with the chemical reaction as written. Okay? Okay pa? Do we follow so far? So we're writing how much energy is required by a given reaction. So it's just doing stoichiometry. Now, how do we actually get to measure things like this? Like how much heat is released by exploding a gummy bear, or how much heat is absorbed by ice as it melts into liquid water? All of these processes, physical or chemical changes, are all measured via an analysis called calorimetry. Okay, so calorimetry is how we actually get to measure the heats of a reaction. And we do so by having our system surrounded by a very controlled set of surroundings. The surroundings that we personally super calibrated and measured and can monitor via certain instruments, like by having a very precise thermometer attached to the surroundings. Okay. So the change in temperature of the measuring part of the calorimeter, such as the water and the thermometer, is then it tells us how much heat was involved or transferred into or out of our system enclosed in the calorimeter. Okay. So again, system and surroundings. Okay. So many processes, so most calorimetry processes occurs in a solution of water. And this is very helpful because we know the thermal properties of water. We know how much heat it requires, water requires to heat it up or to cool it. Now we know the specific heat capacity of water. So take for example this, okay. I have a certain chemical reaction happening in water. The chemical reaction itself, so A becoming B, that's our system. But A and B are all dissolved in water. So they're surrounded by water molecules. The solution itself, or the water, is our surroundings. And what happens is that we will measure the change in temperature of the water of the solution. And that tells us how much heat was transferred by the chemical equation or the chemical reaction, either, into the water or out of the water. So let's pretend I have a chemical reaction A becoming B, and it's an exothermic reaction. What does that mean? The A becoming B will release heat. So it will radiate out heat, and what will happen to the water? The temperature increased. What does that mean? Did the water absorb the heat, or did the water release or put heat into the chemical reaction? Yes, the water absorbed heat because the chemical reaction released heat. Okay? And then the amount of heat that water absorbs can be measured using the delta T, di ba? U equals mc delta T. So we know the mass of water in our calorimeter because we put the water there. We know the specific heat capacity of water because we know it's water. The delta T is measured by the change in temperature we literally observe in the thermometer, and then that will give us the Q. And the Q of water is going to be the opposite Q. So the heat absorbed by the water, so the positive heat that's absorbed by the water is the negative Q released by the system, which is the reaction. So by solving the change of energy of water, we can then solve for the change in energy of the system. Okay? The same thing naman happens in the opposite. If it's an endothermic, ba? In an endothermic chemical reaction or physical change, A becoming B will require energy to be inputted kasi nga endothermic process siya. So saan magagaling yung heat na pinapasok sa system for it to undergo the change? The heat that the system will absorb will come from the water. So what will happen to the temperature of the water? The temperature of the water goes down because the water released heat. Okay? Heat was removed from the water. And then the same thing, Q equals mc delta T. This time the heat lost by the water, so negative Q water, is equal to the heat gained by the system. Okay? Now, simple type of calorimeter that we use, and it's very, very useful, and do not underestimate it. So chemists use this all the time. It's simply called the coffee cup calorimeter. And it's called the coffee cup calorimeter because the simplest version of a coffee cup calorimeter is literally two styrofoam coffee cups placed together, stacked, so that there's like an double insulation, and you have a cover, and then you have a thermometer and a stirrer. The stirrer just allows for the chemical reaction to occur nice and homogeneously, and the thermometer will just tell us how much the water changed temperature. The reaction is the stuff dissolved in the water. The surroundings that we're measuring per se is the water. Plus, of course, everything else. Okay? There are more expensive calorimeters. So once you go into more advanced industry or research work, then you will use the electronic or commercial calorimeters. But essentially, they're the same thing. They're just more insulated. They have better mixing devices, so it's like a motorized mixer. They have more precise thermometers rather than just you having to read a physical thermometer. Okay? So let's now do a very, very easy calorimetry problem. So the physical or the process that we're going to measure is a hot piece of metal becoming colder. Boring, diba? So I have a hot piece of metal and we put it in the water of the calorimeter, and then the metal will cool down. So with that, alam natin, and even if we do the experiment, we know that the hot piece of metal, once it goes into the water, the temperature of the metal, M, will decrease. And we know that the water, from room temperature, its temperature will increase. So can you tell me, how does the heat flow? From where to where? The heat goes from M to W. So M will have a negative heat or positive value for heat. M is negative Q or positive Q? Negative Q. And then see, water will have a positive Q or negative Q. So water gains that heat, positive Q. Okay. So the heat lost by the metal will be the heat gained by the water of our calorimeter. So let's use this. I have 360 grams of steel, of rebar, and I drop it into 425 grams of water at 24.0 degrees Celsius. You're mixing it, you're measuring it with a calorimeter. The final temperature of the calorimeter, so when it stops changing, is now at 42.7 degrees Celsius. Calculate the initial temperature of the piece of rebar steel. So medyo mahirap yung item natin dito. What was the original temperature of our steel? Some given for us. The specific heat of steel rebar is 0.449 joules per gram Kelvin or joules per gram degree Celsius, same thing. The specific heat of water is 4.184 joules per gram Kelvin. So again, the heat lost by the hot metal is the heat gained by the water. Negative Q rebar equals Q water. We will then expand the Q expressions. So negative Cm delta T of the rebar is the Cm delta T of water. We will then expand delta T into temperature final, temperature initial. Okay. So this is the, oops, sorry. The heat lost by the rebar is the positive heat gained by the water. This is the C of the rebar steel. This is the mass of the steel, 360 grams. And then we know that the final temperature of the steel was 42.7 degrees Celsius because that's when it reached equilibrium with the water. So that's the T final. But we don't know is the initial temperature of how hot the steel was. For the water naman, this is negative Q rebar. This is positive Q water. We know that the C of water is 4.184 joules per gram Kelvin or Celsius. That's in tables. Sir, um sorry, wait. Guys, when you message me, can you try to message the other account? Kasi magkahiwalay pala sila. So I'm getting confused. I'm getting chats from my iPad different from my ano. Or when you message, please message to everyone. Sir, when do we put negative signs again? When the heat is lost by something. So the hot metal becoming colder metal. That's why the heat, we will negative that loss of energy. Kaya siya negative Q rebar. Okay? And then it's the water from room temperature became slightly warmer water, 42 degrees Celsius. So it from 24, it became hotter. So it gained kaya siya positive Q water. So the components of positive Q water, so remember Q equals C water, mass water, which is 425 grams of water in our container, and then delta T of water. So T final of water is the 42.7 degrees Celsius that everything ended up as. The initial temperature of water is given to us. We know that initially our water was just 24 degrees Celsius. And so solving for everything, properly sig figs, no? And with algebra, we will get that the initial temperature of our rebar was 248 degrees Celsius. Since the temperature can be both positive and negative value, wouldn't adding the plus and minus reverse the signs of the two Qs? Not really. The positive and negative Q, it doesn't really matter. If Q rebar you made it positive, then you have to make negative there. Also, if you want to make everything absolute, you use Kelvin, and therefore all temperatures are positive, Paolo. If you really want to avoid confusions with signs, the ultimate way of working is by using Kelvin. Okay? Again, it doesn't matter which Q is positive or negative. They just have to be opposite because the heat loss of one is the heat gain of something else. Okay? So that's very important that you add the proper signage. Dapat may times -1 on at least one side. But again, we want to be systematic. Heat loss is where the negative should be. So we will times -1 kung saan yung heat loss process. And heat gain process should be a positive. And therefore, there should be a plus sign there. Okay? You just want to be systematic. Now, if you want to work through these problems more, all of this are just lifted from your chemistry atoms first book. So like I said, the same principles apply to a calorimetry of a reaction. Rather than just a piece of metal cooling down in water, we can imagine the piece of water floating in the metal as the chemical reaction happening within the water. Okay? And so the Q reaction will be the negative Q of solution. Or negative Q reaction is Q of solution. Same thing, because this is really where it's derived from. Q reaction plus Q solution is 0. So pwede rin, this is an endothermic reaction, which means the heat gained by the reaction is lost or taken from the solution. So the solution loses energy. If the reaction is an exothermic reaction, so it's a negative Q reaction, then that's the positive Q gained by the solution of water. Same thing. They mean exactly the same thing. Okay. So this is an example. I'll walk you through it a little bit. We have 50 ml of hydrochloric acid, and it reacts with 50 ml of 1 molar sodium hydroxide at 22 degrees Celsius. So we mix them into our calorimeter, into our coffee cups, and then we will mix it and measure everything. So our thermometer goes from 22 degrees Celsius and it goes up to 28.9. With that said, is our chemical reaction endothermic or exothermic? So the water of our solution went from 22 to 28.9 degrees Celsius. It became hotter. That means that the reaction of hydrochloric acid and sodium hydroxide is exothermic. The question is, what is the approximate amount of heat produced by this reaction of 50 ml plus 50 ml? Okay, so again, the Q reaction is just the negative Q of solution, or negative Q reaction is positive Q solution, same banana. The Q solution is CM delta T, and that's just water, diba? So this is the C of water, mass of water. The mass of water is just the mass of 100 ml of solution, which is just 1 gram per ml. So that's just 100 grams of solution. Okay. And then the delta T of the water, which is our solution. So it was final temp 28.9 minus initial temp 22. Solve for that, you will get 2.9 times 10 to the 3 joules for the Q of solution. That means that the solution gained energy. It gained 2.9 times 10 to the 3 energy. Okay? Which means that the Q of reaction is what? negative 2.9. We just have to take the opposite sign. So the negative sign means the reaction is exothermic. It confirms our original hypothesis that the reaction releases energy to heat up water. Okay? So the delta H of the reaction is negative 2.9 times 10 to the 3 joules, or 2.9 kilojoules. Now, there are very specific types of enthalpies or very specific types of reactions. So the first one is called a combustion reaction. Again, it's when substances react with oxygen to produce carbon dioxide and water. So the heat associated with this process is called the heat of combustion. Another kind of reaction is called the formation reaction. And the formation reaction is just creating a certain compound from standard state elements. So potassium bromide being made from potassium and bromine, or carbon dioxide being created from carbon and oxygen, stuff like that. Okay. You also have the enthalpies of physical changes like melting, which is more properly known as fusion. So the heat of fusion is just going from solid to liquid of substance. And then you also have the heat of vaporization. So vaporization is just turning something from liquid to gas. So the delta H associated with all these processes are very special forms of delta H. Some of these we can put or we can do directly inside the calorimeter. Most of these, however, we can't. So what happens, or how do we get the delta H values of reactions that we can't do in a coffee cup or in even in an expensive calorimeter? Some reactions are just impossible to contain. We will use other means. So we will use calculations rather than experiments to determine their enthalpies. And this is when we use Hess's law. Okay. So Hess's law simply means that if a process can be written as the sum of several stepwise processes, the enthalpy change of the total process equals the sum of the individual steps. Okay? So remember, energy to, di ba? Let's say we have an exothermic process. So going from initial state to final state, we will use this much. So we have delta H equals negative X. Okay? So sometimes it's impossible to do the whole process from the initial to the final. And sometimes we will know reactions that will take us step by step into that state. Hess's law simply means that this whole value of delta H is just the sum of these small delta HA, delta HB, and delta HC. Ganun lang siya. We can show a big reaction as being a sum of smaller sub-reactions or steps. Okay? Because enthalpy changes depends only on where a chemical process starts and ends. It does not take or doesn't care on the path that you took to solve for that delta H. Now, for example, okay, we can think of the reaction of carbon with oxygen to form carbon dioxide. And the direct process is carbon plus oxygen gas becomes carbon dioxide. And its delta H is negative 394 kilojoules. So it releases this much energy. Now let's look at the indirect two-step process, where carbon can react with half a mole of oxygen to become carbon monoxide first. Then carbon monoxide can react with half a mole of oxygen gas to become carbon dioxide. Each of these steps will have their own enthalpies of reaction. If I sum both steps, okay, well, how do I sum both steps? I will simply write all of the reactants here, then put all the products there. Okay? Or systematically, para wala kang redundant substances, we will look at the net change. Okay? So you will cancel out any like terms on both ends. So like here, the product of carbon monoxide can be canceled out because carbon monoxide on the second step was used up. Okay? And then any redundant terms can be added accordingly. So here, half an oxygen on one reactant side, half another oxygen on another reactant side. These two halves of oxygen just add up to become 1 mole of oxygen. Everything else that's untouched will just go down accordingly. So carbon is there, carbon dioxide is there. So you end up with the same net reaction. How about the energy? The energy is simply just the sum of all the individual small steps. So ganun lang din. Negative 111 kilojoules, negative 283 kilojoules. If I sum them up, it's negative 394 kilojoules. The same as with our direct process. So that is basically Hess's law in practice. That you can express one big chemical equation as a sum of smaller chemical reactions, and the overall change will still be the same. Do we follow so far? Now, sometimes, okay, for us to be able to achieve the proper net change, sometimes we have to reverse some reaction steps. Sometimes we have to multiply them by 2 or 1/2. So what happens to the signs or to the values of H? So we have to go back to our molar understanding of stoichiometry and energy, diba? You can treat the energy stoichiometrically as well. So if I reverse the reaction, what happens to the delta H? What happens to the sign? We also have to reverse the sign. If let's pretend to be able to balance out the oxygen, I have to multiply everything by 2. What will happen to the value of this enthalpy? I also have to multiply that by 2. And then once you've come up with the combination of reaction steps with the proper cancelability and it sums to the key equation that you want to study, you can then proceed to sum up all the individual delta H contributions. Okay? Now, sometimes we will not always have all of the chemical reactions that we need. Sometimes you will just know all the potential reactants and products that this chemical equation will have. And for that, we can actually use the enthalpies of formation to come up with the enthalpy of reaction. So what is an enthalpy of formation? As I said a while ago, a formation reaction is a reaction that tells us how a certain compound is created from its elements. So like carbon dioxide is created from carbon reacting with oxygen. And the enthalpy of formation is given as a delta H naught with an F to mean formation. These are usually given in tables, so you don't have to memorize any of these. No, you will just look for these tables, and different substances will all have different enthalpies of formation. Now, can anyone notice any trend here? What happens, or what can you say about the enthalpy of formation for a pure element? like Cl2 or O2 or N2 or sulfur or carbon and graphite, 0. Okay? The standard form of an element, to form it, you don't need any more energy because it's already standard. Okay? But for everything else, for compounds or for certain forms of an element, like diamond or a different kind of monoclinic, okay, or gaseous Cl na at monoatomic, meron silang formation value because they are non-standard forms of an element. So ingat lang. So please take note of the state of an element. Okay. How do we use Hess's law and standard enthalpies of formation? It's very easy. Okay. The delta H of a reaction is just the sum of the standard enthalpies of all the products multiplied by their molar coefficient, stoichiometric coefficient, minus the sum of all of the enthalpies of formation of your products multiplied by their respective coefficients. Let's put this into practice para magets nyo. Okay. I have a chemical reaction here. 3NO2 plus H2O becomes 2HNO3 and 1NO. What is the enthalpy of reaction? We are given all of the enthalpies of formation for all these substances. So what do I do? Delta H not of the reaction equals the sum of all of the delta H F's of the products times their coefficients. So what are our products? HNO3 and NO, diba? Sorry. And then these are our reactants. Okay. So our products, let's start with HNO3. What is its molar coefficient? Its stoichiometric coefficient? 2. Okay. You can even put 2 moles. What is its enthalpy of formation? 207 negative. So please pay attention to the signs. Negative 207.4 kilojoules per mole. And then let's add the next product. That's 1 mole NO. So this is HNO3. Times 90.2. So positive 90.2 kilojoules per mole. Okay. So we will group all of this together. Now we will subtract the sum of all of the reactants and their respective coefficients. So that's 3 moles NO2 times positive 33.2 kilojoules per mole plus 1 mole H2O liquid times negative 285.8 kilojoules per mole. Close bracket. The brackets are very important, okay? That means that you have to create the sum of all of the red, solve for the sum of all of the purple, and then you will subtract the the green from the red. Okay? And with that, you'll then have the delta H for the reaction. Is the process clear to everyone? So this is the second way of using Hess's law. Instead of having a bajillion chemical equations that you will have to cancel out and flip things and whatever to sum everything to the final chemical reaction we want to study, sometimes we can just use the enthalpies of formation and use this formula. Okay, this is the second way of using Hess's law. Okay, we still have time. Yeah, we do. Now, so far, we've been looking at the flow of heat now in the universe. And we think that, okay, heat can go in, heat can go out, and whatever. That's so easy. Work can be done on or done by, and wala lang, energy is just constantly changing forms. Do note, however, that the energy flow of the whole universe is limited to one direction. Okay? From a very high, ordered, compact state of energy into a very spread out state of energy. So energy that's dispersed and spread out. It literally is how the universe began. You had all the matter and energy of the universe condensed into a single singularity, a single point. And then boom, the universe began by that starting to expand, by exploding. And until now, the universe continuously spreading about. The universe is expanding, diba? That's how energy likes to act. It likes to go from concentrated energy to dispersed energy. And that's also the basis of the second law of thermodynamics. So there are videos I want to show you. You can view them. They're all embedded in your modules. But I will show you guys 3 of the 5 videos. Okay? Just please tell me if you can hear the audio or not.
The universe as a whole evolves towards increasing entropy, or disorder, a tendency physicists call the second law of thermodynamics. This movement towards disorganization might lead you to think that organized structures, like, say, living beings, would never spontaneously come into existence. Of course, entropy can go down in part of the universe. You can trade a decrease of entropy in one place, like cooling water so that it crystallizes into ice, for an equal or larger increase in entropy somewhere else, like heating the back of your fridge. Order increases here, but only at the cost of decreasing order there. But we can still ask, why do intricate, complex structures come into being in the universe if the overall tendency is toward increasing disorder? The secret is that order and complexity are very different ideas. Entropy measures how many different ways you can make an arrangement of small-scale particles that have the same large-scale properties, like 37 degrees Celsius, brown hair, good at soccer, and so on. There are lots of different ways. Complexity, on the other hand, is a measure of how hard it is to describe a set of large-scale properties. Simple systems are easy to describe. Complex systems require a lot more information. For example, take a cup filled with half coffee and half milk. It starts off in a state with relatively low entropy. You could swap coffee molecules with each other, or milk molecules with each other, without changing things substantially. But if you swapped coffee molecules with milk molecules, that would be a noticeable change. It's also a simple setup. Milk on top, coffee on the bottom. Now, as the milk and coffee begin to mix, entropy goes up. Where they are mixed together, swapping some coffee molecules for milk molecules no longer makes much of a difference. But the system also becomes more complex. To describe what you see, you would have to specify exactly how all of those tendrils of milk and coffee intricately swirl into each other. Continuing on, entropy keeps going up until the milk and coffee are completely mixed together, and swapping any molecules of coffee and milk with any others doesn't really make any difference at all. That's equilibrium, where there are huge numbers of arrangements of the molecules that look essentially the same. But this highly mixed equilibrium is once again simple. It's just a homogeneous mixture of coffee and milk, no more complicated fractal swirly stuff. This general principle is borne out time and time again. While entropy increases, complexity initially grows, then decays. Complexity can be a natural step along the path to increasing entropy. The best example is the universe itself. The early universe was very smooth and very dense. That's low entropy and also extremely simple. The far future will be smooth again, but very dilute. That's high entropy and again, extremely simple. It's now, in the medium entropy middle, that things look complex. Stars and galaxies, and veins of minerals and rock, and swirling clouds, and amino acids, and proteins, and human beings, and cats. We're at the exciting, beautiful stage of the coffee mixing. But just as with the coffee and the milk, in the far distant future, complexity will decrease again, and complicated stuff like us will at last be simplified out of existence.
So, that's kinda like the scary truth that the universe will end. And I want to show you guys more videos that sort of say the same thing, or explain this or expound on this more.
The Earth receives about 90 petajoules of energy from the Sun every second. That's a lot, enough to satisfy all human energy needs thousands of times over. However, the Earth also radiates an equal amount of energy back into space as heat. An almost equal amount anyway. The Earth is gradually heating up, but that's another story. So if energy in equals energy out, how can we possibly be using any energy to do anything? What matters, it turns out, isn't simply energy, it's useful energy. And energy is useful when it comes packaged in a low entropy form. The total amount of energy in any closed system can't change, of course. Energy is conserved. But that energy can be in different states of usefulness. There's useful energy in the water behind a dam, which will flow until the level is the same on both sides, but will never go back up. Or in hot tea, which will melt a cold ice cube until they reach a medium temperature. You never see tepid tea spontaneously generate an ice cube while heating up, even though the total energy would be the same. So useful energy is low entropy, out of equilibrium energy that can be put to work to turn a turbine or push a piston or melt an ice cube. Useless energy, meanwhile, can't be put to work. It's out there in the form of waste heat or noise or the potential energy of a ball just sitting on the ground. We can't really do anything with it. For example, gasoline and air carry useful low entropy energy. By burning them together, we can accelerate a car, drive for a while, then put on the brakes and stop. The total energy of the world remains constant during the trip, but useful chemical energy is converted into useless high entropy heat and noise. The energy is still there, but we can't reclaim it to power any more cars, as convenient as that would be. And thus it is with the Earth. The Sun sends us energy in a convenient, useful, low entropy form, mainly as photons of visible light. This energy gets absorbed and used and degraded by various processes here on Earth until we radiate it away in a much higher entropy form. Lots of infrared photons. For every visible photon we receive, the Earth radiates about 20 infrared photons out into space. Even though there's a balance of energy in with energy out, the entropy of the energy has gone up 20 times. The Sun, in fact, is only a source of useful energy because it's a hot, bright spot in a cold, dark sky. If the whole sky were the temperature of the Sun, our planet would receive a lot more energy, but the Earth would quickly average out to a state of high entropy equilibrium, with everything at the temperature of the Sun. So things like driving or living would be impossible. Not because there's insufficient energy, but because you can't do anything when all the energy has averaged out. In equilibrium, all energy is equally useless. Nothing ever changes, and time's arrow ceases to have any meaning.
Hey, Henry here. Thanks for watching. This is the fourth
So in the second video, it was hinted that there is directionality to the universe, that we always want to go from high entropy energy states to low entropy energy states, and that eventually the energy state of the whole universe will be equal. And that is what we call the heat death of the universe. Now, because time is linked by change, diba? We know time has passed because change has occurred. That you were able to take another breath, that you were able to watch something change or listen to something, diba? When all energy in the universe has equalized and equilibrated with the rest of the universe, time will stop because nothing can change anymore. So literally, the universe as you know it will end. Scientifically, meron niyang end of the world. But don't worry, it's like a bajillion years away from now. Okay? Let's watch this last video.
Astrobiologist Michael Russell once said that the purpose of life is to hydrogenate carbon dioxide. Or as Nobel Prize-winning physiologist Albert St. George put it, life is nothing but an electron looking for a place to rest. While these aphorisms might not capture the meaning of life that most of us look for, their point is that living organisms ultimately depend on and facilitate the universe's tendency to increase entropy. That may seem counterintuitive, since living beings are themselves highly organized, while entropy is a measure of disorder. But as we know, complexity is not the same thing as order. Every organism, just by living and breathing, acts to increase the entropy of the universe. Think of a photon arriving from the sun, packed with useful energy. It can be captured by a plant or microorganism that uses photosynthesis to store that energy in the form of sugar. But the sugar doesn't contain quite as much useful energy as the original photon. Some of the energy ends up heating the plant and its environment. An animal, like us, eats the sugar and uses its energy to create molecules of ATP, adenosine triphosphate. ATP is like a little power pack of energy that can be sent to a part of the body where it might be helpful. But ATP doesn't have quite as much useful energy as the sugar that went into making it. Some of that useful energy got lost pushing around all the cell machinery that makes the ATP. The proteins in your muscles utilize the energy in ATP to contract, so that you can lift a barbell or a slice of pizza. But not all of the useful energy of the ATP goes into lifting the pizza. As before, some of it is degraded into noise and heat. Not only that, ATP's useful energy can also be used to repair broken down cells or organs, again becoming less useful in the process. The pattern here is obvious. Every step along the way, the energy in that original photon is gradually degraded, entropy increases, and at the end, all that's left is an organized but slightly warmer plant and cell and muscle, plus some high entropy infrared light that gets radiated out into the universe. Energy transforms from useful to useless in the cause of keeping organisms like us alive. In fact, life itself may have arisen because of entropy. The early Earth had pockets of low entropy conditions full of useful energy, like warm alkaline vents on the ocean floor. But there may have been no simple chemical reaction that could take advantage of that energy, use up its usefulness, and allow the entropy to increase. There were, however, more complicated chains of reactions that could do the job. In just the right circumstances, an appropriate network of chemical reactions might find a way to sustain itself by tapping into the useful energy in its environment. Some networks might have become embedded in molecular membranes, the precursors of cell walls, and broken away from their point of origin, becoming the first living organisms. Maybe that's how life began. A complex combination of chemical reactions that figured out how to tap into otherwise unavailable useful energy. We can tell a similar story about why stars shine. Hydrogen nuclei have a ton of useful, low-entropy nuclear energy to release, if you can get them to fuse together into helium. But there's a big barrier to getting that to happen. Fusion is hard. And yet, the cores of stars do the job marvelously. So stars, like life, also survive because of the increase of entropy throughout the universe. Our sun takes a low-entropy fuel source, hydrogen nuclei, and converts it into higher entropy energy, photons of visible light. Life takes that higher entropy energy as a fuel source and converts it into even higher entropy energy, photons of infrared light. In a very real sense, the purpose of life is to continue the mission of the stars.
Hey, Henry.
So there is the second law of thermodynamics in what I think is in a more beautiful put way now, rather than just all the numbers again that we've been taking up. It just gives you a process, or it gives you really what's happening in the universe and how all of what we're studying here with chemistry and energy and biology and physics are all related, and even your very existence. So one of the major takeaways I want you to all to take is that energy flow in the universe will always lead to the increasing levels of useless energy. So always start from more concentrated, useful, low entropy energy, and then we always end up creating useless energy like dissipated heat, infrared rays, stuff like that. Okay? So although the energy of the universe will always be conserved, the amount of useful energy of the universe is finite. And like I said before, eventually, once all the energy of the world is now equally as useless as each other, the universe will stop, time will stop. Okay? Now, when talking about energy dissipating, we talk about the spontaneity of a process. So spontaneous processes, things that readily happen, are when the entropy of the universe increases. Okay? So a process that naturally occurs that does increase in entropy are called spontaneous processes, and a process that does not occur under a specific set of conditions is called non-spontaneous. Please don't confuse spontaneous with observable or fast. Take, for example, the reaction of diamond turning into graphite. So diamond, super hard, super, beautiful stone, turning into graphite, literally the stuff in your pencils. Thermodynamically speaking, so speaking strictly with thermodynamic numbers, just delta Hs and entropy and stuff like that, this process is spontaneous, meaning it's favored by the universe for diamonds to become graphite. But you've been to museums, we've seen ancient diamonds. We know the diamonds have been formed bajillions of years ago, and yet they're still diamonds. I don't recall ever seeing a diamond that's starting to turn black. And this is because at normal temperature, so the diamonds we have let's say in our presence, now in this normal room temperature, in our pressure that we have here, which is just 1 atmosphere and sea level, the rate of this reaction is so immeasurably slow. Okay? It's ridiculously slow that it's as if it's not happening. Now, this process can actually be observable, but you need to bring up the temperature to extreme values like 1000 to 2000 Kelvin. So yun. Iba yung fast, which is kinetics, sa spontaneous, which is thermodynamics. So part 2 of our module 2, diba, was kinetics, how fast things happen. That's kinetics. Now we're taking thermodynamics. And these two sometimes don't agree with one another. Okay? But they are both related and they're interlinked, which you'll see at the end of your module 2. So many spontaneous processes in our universe, occur because they release energy into the surroundings, and sometimes they release energy nga as infrared heat. So spontaneous processes are often exothermic, but not always. So let's take this example. I have at room temperature and a pressure of 1 atmosphere, solid water becoming liquid, so ice becoming water, and it has a delta H of positive 6.01 kilojoules per mole, or liquid becoming solid with a delta H of negative 6.01. Sorry, nabaliktad ko ata yung signs. Which is spontaneous? One that releases energy or one that gains energy? Let me go ahead and change the signs here. Sorry. Tama, exception nga pala to. You might think, diba, that releasing energy should be spontaneous. But did you ever see at room temperature water becoming solid water, even though it dissipates energy? At room temperature, what is more likely to be a spontaneous or thing that you observe? Water becoming ice or ice becoming water? What's for you? What feels natural? At room temperature at 25 degrees Celsius, at means at your room right now, what can you observe more happening easily? Ice melting or liquid water magically becoming ice in your room right now? Ice melting, diba? But if you look at ice melting, okay, solid compact molecules, they have to start moving around to become liquid. So they have to gain energy. Hmm. Eh, sabi natin that gaining energy is typically not spontaneous and typically releasing energy, which is liquid water becoming solid water, should be the one spontaneous. So, with that said, it's not just about the release of heat that determines spontaneity. Okay? So, although it makes sense that it's generally true that we want to release energy into the universe, that's not all that we have to look at. So, it's not just enthalpy that determines spontaneity. We need to look at the contribution of entropy. So remember, an increase in entropy is always favored. That's how the universe likes to go, from ordered to highly disordered and spread out. And it just so happens that solid water or ice is a very low entropy state. And liquid water, where the water can really move around and disperse the energy into a lot of positions, is a higher entropy form. That is why it's going from solid ice to liquid water. That was the spontaneous process. It has the adequate increase in entropy. Okay? And furthermore, even liquid water, even in room temperature, it actually starts to evaporate. That's also a spontaneous process, is going from liquid to gas, which is an even higher entropy state. Entropy can be measured by the delta H of a system divided by its temperature. So by that formula. And that again, the second law of thermodynamics states that it's the delta S of the universe that's increasing. So just like with delta H, the delta S of the universe is the delta S of the system, but also the delta S of the surroundings. So any spontaneous process is where the entropy of the universe is increasing. And a non-spontaneous process is one wherein the delta S of the universe is decreasing. If a process at equilibrium, no observable changes, delta S of the universe is unchanged as well. Now, the third law of thermodynamics is sort of important in helping you understand the second law. And that's just that the entropy of any perfectly crystalline solid is at 0 degrees Kelvin is 0. So it has no entropy. And with that, just like with enthalpy, we have standard entropies of substances. So different substances will have their own entropy values. And it's an absolute S. And to get the delta S, just like with the delta H, we simply have to do all the entropies of the products times their molar coefficient minus the sum of all the entropies of the reactants minus their molar reactants. Okay? Now, to get or determine the spontaneity of a process, you need to know the delta S of the universe. And that's quite impossible. That's very, very, very difficult. So what we do instead, okay, is that we look at free energy, which looks at the enthalpy change of a system and the entropy change of a system. Okay? Or the surroundings rather. And that free energy change will also determine whether or not a process is spontaneous or not. It coalesces or puts together the enthalpy, meaning is energy released into the universe or gained by the system, and is entropy for the system increased or decreased at a given temperature. Okay? And ganun din siya. If the free energy is negative, so delta G is negative, a process is spontaneous. If it's positive, it's non-spontaneous. If it's zero, it's equilibrium. Okay? Sige. I think it's 3 o'clock. There's just like a few more slides left, and I think it's very easy. So what I want you to do na lang is, I think with your understanding of enthalpy and with your now new understanding of some of the basics of entropy, no, especially just solving for the entropy of formation of a substance using standard entropies, you'll be able to then plug in all of those values now into a free. Am I not screen sharing? Oh my god, I am not. Sorry. My screen sharing stopped. Okay, sorry. My internet must have removed it. Okay, so last, yun lang. Just by solving for entropy, okay, of a system without having to solve for the entropy of the universe, multiplying that by the temperature, and subtracting that from the enthalpy change of of the process itself, the system itself, we can denote the delta G, the free energy change of a system. And if this is negative, then the process is spontaneous. If it's positive, then it's non-spontaneous. And if it's zero, then the system is at equilibrium. This free energy, I think you can study this on your own. It's all there in your module. Okay, I'm sorry about that again. If you have any questions about how to understand free energy and how to solve for items, you can just message me. But I think with your understanding now of enthalpy and Hess's law and how to apply or how to do all the thermodynamic calculations with stoichiometry and stuff like that, I think you should all be good now for answering your problem set. Okay? Sige. Sorry about that. Nawala yung screen a while ago. Okay. Yes, Izio, you have a question?
Hello, sir. Am I audible? Hello, sir. Am I audible?
Sorry, I can't hear. Izio, you have a question?
Hello, sir. Am I audible?
Ayun, now I can hear you. Sorry
Okay.
guys, super sama na talaga ng internet ko. Yes?
Good afternoon po, sir. Just wanted to bring up a concern regarding the midterm schedule. So a lot of classmates have asked me to if it would be possible to reschedule po the midterms to a later, preferably non-weekday date.
Sorry, what?
Uh, if it would be possible to reschedule the midterms.
I cannot because it's for all other sections are sticking and it was given to you at the start of the semester.
Oh, I see.
So you had the whole semester. It was already set. It's gonna be April 2.
Thank you, sir.
Okay? So you have the whole day. It starts at very early in the morning, it ends very late at night. And you just need 4 hours or even less to answer it. So even the 4 hours we're giving is super generous already. Just for of several items. Okay?
Thank you,
Yes,
sir.
Ella, you have a question?
Sir, I would just like to ask something po regarding din sa latent heat of fusion po. Pag po sa
Sorry,
mga
what?
Sa latent heat of fusion po, yung may mga physical changes po. Paano, meron din po ba yung positive and negative signs po?
Yeah. So, kapag, here, let's go back. Types of enthalpy. So let's pretend the heat of fusion, this will usually be a positive value because heat has to be absorbed by something solid to become liquid, diba, Ella? Now, what's the opposite of fusion or melting? O desolidifying or ano ba ang term? Freezing, diba? So delta H of freezing is the negative of delta H of melting or fusion.
Okay.
Heat of evaporation is again usually positive because you need heat to turn liquid substances into gaseous substances. So delta H vap is usually a positive value. But what's the opposite process of evaporization? Well, it's condensation. So delta H condensation will be the negative value of delta H vap. Gets?
Yes po, sir.
Oo, ganun lang siya. Sir, I have to go. Yes, anyone, if it, again, at 2:50, no matter if I'm done or not, you feel free to leave and I'll just post the recording. Any other questions? Sorry, I really tried my best to go until free energy. I think we were to do as much as we could. But yeah, I just have to remind everyone this course is primarily self-study. None? Okay, thank you for your question, Ella.
Thank you, sir.
Thank you, sir.
Sige po. You have a question, Paula? I think not.